In this video, I introduce a scaling law for large AGI models. Scaling law guides to obtain the near optimal performance of large language models, which can probably select the model skill and the data skill based on the commit budget. It's a well-known factor that LLM performance can be improved with increasing commit budget, model skill, and data skill. The model skill can be represented by model non-embedding parameters and the data skill by the number of tokens. Scaling law optimizes the allocation between model and data skills for a given commit budget, as shown here. LLM performance improves smoothly as increasing the model skill, dataset skill, and amount of computer resource used for training. For optimal performance, all three factors must be scaled up in tandem. For example, the scaling law can be used to predict the performance of DeepSeek 7 billion and 67 billion models, as shown here. Suppose that commit budget and model size have a parallel relationship. The LLM loss L can be expressed as here, where the first term depends on the model size, second term depends on the data set scale, and the third term captures the loss for an ideal model on the infinite data. To estimate ABE alpha and beta, we minimize the Hoover loss, which is defined as here, where L hat is the final pre-trained loss, and delta is said to be 10 power minus 3, which is robust for outliers. By minimizing the loss error, we can get efficient computational frontier to find the scaling law. If we select the E, A, B, alpha, and beta values, the LLM model with 70 million parameters trained on 1,400 billion tokens of data has a loss 1.936, which means that each model parameter requires 20 tokens. For a fixed set of non-different training flop count, we vary the model size and consider the final training loss for each point. The goal is to select the optimal parameter count to find the scaling law. For each flop budget, the model is trained to plot the final loss against the parameter count. In all the cases, we ensure that we have trained a diverse enough set of model sizes to see a clear minimum in the loss, as shown here, and so on. We fit a parabola to each ISO flops curve to directly estimate at which model size the minimum loss is achieved. We then fit a power law between flops and loss optimal model size and the number of training tokens, as shown here. These points are used to find the model parameters and the data skill given a commit budget. Bits per byte metric measures how many bits are required to encode a byte of data. Small bits per byte has a maximum entropy. Therefore, the LLM models with a small bits per byte on the validation set can be generalized well according to the principle of maximum entropy. Cross entropy between two probability distributions, P and Q, measures if an average number of bits needed to identify a data coding model is optimized for estimated probability distribution Q. For discrete P and Q on the support X, the cross entropy of V relative to P over the support X is defined as here, where B is the base of the logarithm common values of B 2E and 10, which correspond units of entropy to be the base for B is 2. Net for B is E, and the bands for B is 10. The base property is defined by the cross entropy with B is 2. Namely, the probability distribution Q is first encoded as a base and then compared with the true distribution P. If base by property is defined as a loss function, the optimization objective is to minimize the number of bits for byte of data. For more details, please check with these references. Thank you. Bye.